Welcome to this problem walkthrough. Today, we'll be tackling the problem number 1298, maximum candies you can get from boxes. Together, we'll break down the problem, explore various approaches, and arrive at an optimal solution. Let's dive in. In this problem, you are presented with several boxes, where each box is uniquely identified by an integer. These boxes can contain three things: candies, keys, and other boxes. If a box is unlocked, you can open it to collect all the candies inside, and you also gain access to any keys and contained boxes it holds. However, if a box is locked, you cannot open it unless you have the corresponding key. To maximize the number of candies you can collect, you need to determine the optimal way to open boxes using the resources available. To start, you are given a set of boxes that are initially accessible, and the task is to figure out how to collect as many candies as possible by leveraging the keys and unlocking additional boxes as needed. Remember, the order in which you open boxes matters, and you can only open a box if it is unlocked and accessible. The inputs for this problem include several arrays. First, the status array indicates whether each box is initially unlocked, with a value of 1, or locked, with a 0. The candies array specifies the number of candies inside each box. Then, the keys array describes which keys are contained in each box, where keys, I, is a list of keys that can unlock specific boxes. Similarly, the contained boxes array lists the boxes inside each box, meaning contained boxes, I, contains the indices of boxes that are accessible only after opening box I. Finally, the initial boxes list specifies the boxes you start with. The output for the problem is a single integer representing the maximum number of candies you can collect based on these inputs. Let's explore some examples to understand these rules better. In the first example, the input specifies that there are 4 boxes with different initial statuses: candies, keys, and contained boxes. Starting with box 0, which is initially unlocked, we open it to collect 7 candies and gain access to boxes 1 and 2. Box 2 is also unlocked, so we open it next to collect 4 candies and obtain a key for box 1. With this key, we unlock and open box 1, where we collect 5 more candies and gain access to box 3. However, box 3 is locked, and we don't have its key, so we cannot open it. In total, the candies collected are 7 from box 0, 4 from box 2, and 5 from box 1, giving us a maximum of 16 candies. In the second example, we start with box 0, which is initially unlocked. Opening it allows us to collect 10 candies and gain keys for all other boxes, specifically, boxes 1, 2, 3, and 4. Using these keys, we unlock and open all the remaining boxes. Box 1 contains 20 candies, box 2 holds 30, box 3 has 40, and box 4 contains 50. By opening them sequentially, we collect all the candies, resulting in a total of 10, 20, 30, 40, and 50 candies, which adds up to 150 candies. In the third example, starting with box 0, which is initially unlocked, we open it to collect 1 candy and obtain the key to box 1. Since box 1 is already unlocked, we open it to collect 2 candies and gain the key to box 2. Using this key, we unlock and open box 2, collecting 3 candies along with the key to box 3. Finally, we use the key to unlock and open box 3, where we collect 4 candies. The candies collected from all boxes are 1, 2, 3, and 4, resulting in a total of 10 candies. This example demonstrates how unlocking boxes in sequence can maximize the collection of candies. There are a few important constraints and edge cases to consider. For instance, if the initial boxes list is empty, then there are no accessible boxes, and you must return 0. Similarly, if all the boxes are locked and there are no keys available, you cannot open any boxes, so the result is also 0. Another scenario involves circular dependencies, where a box might contain itself or boxes are mutually dependent on each other. The algorithm must handle such cycles without causing errors. Additionally, duplicate keys or boxes may appear, and the solution must ensure that this redundancy does not lead to unnecessary operations or incorrect results. These considerations ensure the solution is robust and handles all possible edge cases effectively. To solve this problem, one approach we could consider is the brute force method. The idea here is to repeatedly go through all the available boxes, looking for any that we can open with the keys we currently have. Once a box is opened, we collect its candies, add any new keys to our set of accessible keys, and identify any additional boxes it contains. This process is repeated until no unopened boxes remain or no more keys are available. While this approach is straightforward and easy to implement, it has significant limitations. The main drawback is its inefficiency. It requires repeatedly scanning the entire list of boxes, which results in a time complexity of n squared, in the worst case, where n is the number of boxes. This makes the brute force method impractical for large inputs, as the repeated scanning leads to poor performance. However, by analyzing the problem more closely, we can identify a more efficient solution. Specifically, we can treat the boxes and their relationships as a graph, where keys unlock new nodes, and use a breadth-first search, or BFS, to explore this graph systematically. BFS is particularly well suited for this type of problem because it allows us to explore all reachable nodes in an organized and efficient way. The key insight here is that the problem is fundamentally about exploring all boxes that are reachable from our starting point. BFS gives us a structured way to do this while avoiding redundant work. Here's how we can implement it step by step. First, we'll use a queue to manage the boxes we can open, ensuring that we process them in a logical order. We'll also use two sets, one to keep track of the keys we currently have and another to store unopened boxes that we discover along the way. Initially, we start with the boxes that are already available to us, collecting their candies and adding any new keys and contained boxes to our respective sets. Whenever we gain a new key, we'll check if it can unlock any previously inaccessible boxes. If it can, those boxes are added to our queue for further processing. This process continues until no more boxes can be opened. The complexity of this BFS approach is much better than the brute force method. Each box is processed exactly once, leading to a time complexity of n, where n is the total number of boxes. The space complexity is also n, as we use the queue and sets to manage our data. This method is efficient, avoids redundant scans, and scales well even for large numbers of boxes, which is why it's a much better choice. Given the efficiency and clarity of the BFS approach, it is the most suitable strategy for this problem. Unlike the brute force method, BFS systematically explores all accessible boxes without repeatedly scanning the entire list. This reduces the time complexity from n squared to n, making it far more practical for larger inputs. Additionally, BFS provides a clear structure for separating accessible boxes, collected keys, and unopened boxes, which aligns perfectly with the constraints of the problem. In essence, this approach leverages graph traversal techniques to model the problem effectively. While the brute force method might be easier to grasp initially, it is computationally impractical for larger datasets. BFS, on the other hand, strikes the perfect balance between readability and performance, making it the ideal solution for maximizing the candies we can collect from the boxes. To solve this problem, we need a structured strategy to navigate through the boxes and collect the maximum number of candies. First, we initialize key data structures. A queue will help us manage the boxes we can currently open, ensuring a breadth-first traversal of the boxes. This is important because it allows us to systematically explore each box and its contents. Next, we use a set to store the keys we collect, as this enables efficient lookup and ensures we don't duplicate keys. Additionally, we maintain a visited set to keep track of boxes we've already opened, preventing unnecessary reprocessing and ensuring we avoid infinite loops. Finally, we populate the queue with the list of initially opened boxes and set up a variable to track the total number of candies collected, which starts at 0. With these foundations in place, we can begin processing the boxes and collecting candies. The next step is to process the boxes in the queue. While the queue is not empty, we retrieve the next box for processing. If this box has already been opened, we skip it to avoid redundant work. Otherwise, we mark the box as opened by adding it to the visited set. At this point, we add the candies from the box to our total candy counter. Then, we collect any new keys found in the box and add them to our key set, which expands the range of boxes we can potentially unlock. Now, for each new box discovered inside the current box, we check if it's either unlocked or if we already have the key for it. If either condition is true, we add it to the queue for further processing. This ensures that all reachable boxes are explored. For locked boxes where we don't yet have the key, we temporarily skip them but keep them in mind for later. If we eventually find the required key, we can revisit these skipped boxes to unlock and process them. The algorithm continues until there are no more boxes left to process in the queue, at which point it terminates and returns the total candy count. There are several key insights that make this algorithm both effective and efficient. First, the use of breadth-first search, or BFS, allows us to systematically explore the boxes layer by layer, ensuring that all reachable boxes are processed. This systematic approach is critical for handling the dynamic nature of the problem. Second, the use of a set for keys ensures that checking whether we have a specific key is extremely efficient, operating in constant time on average. Third, the visited set plays a crucial role in preventing the reprocessing of boxes we've already opened, which not only saves time but also eliminates the risk of infinite loops in cases where boxes reference each other cyclically. Finally, the algorithm dynamically adjusts the range of boxes that can be opened as new keys are discovered, ensuring flexibility and adaptability throughout the process. Together, the queue, key set, and visited set work in harmony to optimize both time and space efficiency. When analyzing edge cases, there are a few scenarios to consider. If all boxes are locked initially and no keys are available, the algorithm will correctly return 0 candies, as no boxes can be opened. In cases of cyclic dependencies, where boxes reference each other in a loop, the visited set ensures that each box is only processed once, avoiding infinite loops. If boxes contain keys but no candies, the algorithm will still function correctly and return 0, as it focuses solely on the candies collected. Additionally, if certain boxes remain unreachable due to missing keys, the algorithm gracefully skips them and processes only the boxes that can be unlocked. From a complexity perspective, the algorithm is highly efficient. Each box is processed exactly once, resulting in a time complexity of O(n). Operations such as collecting candies, adding keys, and updating the queue are all constant time, further contributing to the O(n) time complexity. In terms of space, the queue, key set, and visited set collectively require linear space relative to the number of boxes, making the overall space complexity O(n) as well. This combination of efficiency and adaptability makes the algorithm well-suited for solving the problem. Here, we start by importing the DEET class from the Collections module, which will be used to manage the queue for our breadth-first search, or BFS. Then, we define the solution class and the method maxCandies, which takes several parameters: the status of each box, the number of candies in each box, the keys contained in each box, the boxes contained within other boxes, and the initial set of boxes available to us. Within the method, we initialize 3 data structures. First, we have the queue for boxes that can be opened. This is where we'll store boxes that are ready to be processed. Next, we use a set called visited to keep track of boxes we've already opened, ensuring we don't process the same box multiple times. Lastly, we have a set named collected_keys to store keys we find along the way but haven't yet used to open boxes. Now, we loop through the initial boxes. If a box is already open, indicated by its status being 1, we add it to the queue to be processed. If it's locked, we add it to the collected_keys set, meaning we might be able to open it later if we find a matching key. We also initialize total_candies to 0, which will keep track of the total number of candies we collect. From here, we use a while loop to repeatedly process boxes until the queue is empty. Inside the loop, we take the first box from the queue using popleft. If the box has already been visited, we skip it to avoid redundant work. Otherwise, we proceed to mark it as visited and collect the candies from it. Marking the current box as visited ensures we don't revisit it, and we increment our total candies by adding the candies in this box. Next, we handle the boxes contained within the current box. For each of these contained boxes, we check if it hasn't been visited yet. If it's unlocked, meaning its status is 1, we add it directly to the queue. Otherwise, we add it to the collected_keys set, since we might find the key to open it later. After that, we process the keys found inside the current box. For each key, if it's not already in our collected_keys set or currently in the queue, we add it to collected_keys. This ensures we keep track of all the keys we find as we explore the boxes. Finally, we check if any of the keys we've collected so far can unlock new boxes. For each key, if it corresponds to a box that hasn't been visited and is unlocked, we add that box to the queue and remove the key from collected_keys, as we no longer need it. Once the queue is empty, meaning there are no more boxes to process, we return the total number of candies collected during this process. This way, the algorithm ensures we collect the maximum candies possible while efficiently managing the exploration of boxes and keys. Here, we start by importing the necessary Java utilities and defining our solution class. The method maxCandies takes several arrays as input, representing the status of the boxes, the number of candies in each box, the keys contained inside the boxes contained within other boxes, and the list of initial boxes we have access to. To manage our exploration, we initialize a queue for a breadth-first search, or BFS, along with two sets, one to track the boxes we've already opened and another to store the keys we collect along the way. Additionally, we define a variable total candies to keep track of the candies we collect. We then iterate through the initial boxes. If a box is already open, we add it to the queue, making it ready for immediate processing. If it's locked, we store its key in the collected keys set for potential use later. The BFS loop starts by processing boxes from the queue, and within this loop, we check whether the current box has already been visited to avoid redundant work. Now, when processing a box from the queue, we first mark it as visited to ensure we don't process it again. We then collect all the candies from this box by adding the value from the candies array to our total candies variable. Next, we handle all the boxes contained inside the current box. If a contained box hasn't been visited yet, we check if it's already open. If it is, we add it to the queue for immediate processing. Otherwise, we store its key in the collected keys set. After processing contained boxes, we move on to collecting all the keys found inside the current box. For each key, if it hasn't already been collected or added to the queue, we add it to our collected keys set. This ensures we're ready to use these keys to unlock other boxes. Finally, we iterate through the collected keys set to see if any of these keys can now open new boxes. If a key corresponds to a box that hasn't been visited yet and is currently open, we add that box to the queue for processing. When a key is used to open a box, it's removed from the collected keys set to prevent it from being reused unnecessarily. This process continues until the queue is empty, meaning there are no more boxes left to process. At that point, we've collected all the candies we can access, either directly or indirectly, through the boxes and keys. The method then concludes by returning the total candies value, which represents the maximum number of candies we can collect. This implementation leverages BFS to systematically explore the boxes and manage the dependencies between locked boxes and the keys required to unlock them, ensuring an efficient and complete traversal of all accessible boxes. Here, we begin with an example to understand the basic case. The input specifies an array of box statuses, where 1 means a box is open, and 0 means it's locked. We also have the number of candies in each box, the keys each box contains, the boxes nested within each, and the initial set of boxes available. Our goal is to maximize the candies collected. To start, we initialize the process. The queue is set to contain the initial open box, which is box 0. The visited set tracks the boxes we've already processed, while collected_keys keeps track of the keys we've found. Finally, total_candies will accumulate the candies we collect. At this point, the queue contains only box 0, and everything else is empty or 0. We now process box 0. First, we remove it from the queue and mark it as visited. Box 0 contains 7 candies, so we add this to total_candies, making it 7. Next, we add the boxes contained within box 0 to the queue. Box 2 is directly added because it's open, but box 1 requires a key. However, box 0 provides us with key 1, so we add this key to collected_keys. After processing box 0, the queue holds box 2, and key 1 is stored in collected_keys. Moving on, we process box 2 by removing it from the queue and marking it as visited. Box 2 contributes 4 candies, bringing total_candies up to 11. Since box 2 contains no additional boxes or keys, the queue becomes empty. Now, since we have key 1, we use it to open box 1. This adds box 1 to the queue, and we clear collected_keys as the key has been used. Next, we process box 1. It is removed from the queue and marked as visited. Box 1 contains 5 candies, so we add these, updating total_candies to 16. Box 1 also contains box 3, which requires a key, so we add it to the queue. Additionally, box 1 provides key 3, which is stored in collected_keys. At this stage, the queue is empty again, but we have key 3. Using this key, we open box 3 and add it to the queue, clearing collected_keys once more. Finally, we process box 3. It is removed from the queue and marked as visited. Box 3 contains a substantial 100 candies, which are added to total_candies. The total now reaches 116. With no additional boxes or keys, the process concludes. The output for this example is 116, as we've successfully collected all available candies. In this scenario, we examine a case where no boxes are accessible. The input lists all boxes as locked, with their statuses set to 0. While each box has some candies, none of them contain keys or other boxes, and the only initial box provided is box 1, which is locked. During initialization, we find that the queue is empty because the single initial box is locked and cannot be added. The visited set, collected_keys, and total_candies all remain empty or 0. Since the queue is empty, we cannot proceed with any box processing, and no candies can be collected as a result. Thus, the output for this example is 0. This example introduces a more complex case with interconnected boxes and keys. The setup includes 5 boxes, some of which are initially open and others locked. Each box contains a specific number of candies, as well as keys or other boxes. Here, box 0 is the only initial open box. To begin, we initialize the queue with box 0, as it is open and ready to process. The visited set starts empty, and collected_keys is also empty. The total number of candies collected, total_candies, is initialized to 0. This setup allows us to start processing the boxes systematically. To begin, we process box 0. It is removed from the queue and marked as visited. Box 0 contributes 10 candies, which are added to total_candies, bringing it to 10. Within box 0, we find box 1, which is added to the queue. Additionally, box 0 contains keys for boxes 1 and 2. Since box 1 is already accessible, key 2 is stored in collected_keys. Moving on, we process box 1. It is removed from the queue and marked as visited. Box 1 contributes 20 candies, updating total_candies to 30. Inside box 1, we find box 2, which is added to the queue. Box 1 also provides key 3, which is added to collected_keys. At this stage, the queue holds box 2, while collected_keys contains keys 2 and 3. Next, we process box 2. It is removed from the queue and marked as visited. Box 2 adds 30 candies to total_candies, bringing the total to 60. Inside box 2, we find box 3, which is added to the queue. Box 2 also provides key 4, which is stored in collected_keys. We then process box 3 by removing it from the queue and marking it as visited. Box 3 adds 40 candies, raising total_candies to 100. Within box 3, we find box 4, which is added to the queue. Since box 3 does not provide any keys, collected_keys becomes empty. Finally, we process box 4. It is removed from the queue and marked as visited. Box 4 contributes 50 candies, bringing the final total_candies to 150. After processing all accessible boxes, we find that the total number of candies collected is 150. This is the maximum possible candies based on the given input, as all boxes have been opened and processed. The final output for this example is 150. The time complexity of this solution is determined by the total number of boxes and the total number of keys and contained boxes. Specifically, it's O, n plus m, where n is the number of boxes, and m represents the sum of all keys and contained boxes. To understand this, consider that we first process the initial boxes. In this step, we iterate through the initial boxes array once to determine which boxes can be opened immediately or require keys to unlock. Since we only examine each box once during this phase, this operation takes O(n) time. Next, we perform a breadth-first search to process the boxes. In the worst-case scenario, every box is visited exactly once because after processing, each box is added to a visited set to ensure it isn't revisited. This means the while queue loop will run n iterations. Within each iteration, several operations occur. First, collecting candies is an O1 operation. Then, processing contained boxes involves iterating through all the boxes inside the current one and contributes m time across all iterations, since the total number of contained boxes is bounded by m. Similarly, processing the keys found in a box also contributes m time in total. Finally, checking collected keys to unlock additional boxes also sums to m. When we combine these, processing each box takes O1 for candies and m across all iterations for contained boxes, keys, and collected keys. Adding the n for the boxes themselves, the overall time complexity is n plus m. Now, let's consider the space complexity, which is also n plus m. This is because we need to account for the memory used by several components. First, the queue used for BFS can store up to all openable boxes at once in the worst case, requiring n space. Similarly, the visited set, which tracks all the boxes we've processed, could contain all n boxes, also using n space. Additionally, the collected_keys set, which holds all keys that haven't yet been used, could potentially store all m keys, requiring m space. These are the main contributors to the space usage of the algorithm. The input data itself also contributes to the space complexity. Arrays such as status, candies, keys, and contained boxes need to be stored in memory, and their combined size is n plus m. When we add up the memory usage from the queue, the visited set, the collected key set, and the input data, the total space complexity comes to n plus m. Compared to a brute force approach, where we might repeatedly attempt to process all boxes without an organized strategy, this method is much more efficient. A naive approach would result in a time complexity of n squared, in the worst case, as we might check each box multiple times. However, the BFS-based approach ensures that each box and key is processed only once, achieving n plus m time complexity, which is a significant improvement. When analyzing the best, average, and worst cases, we observe that the time and space complexity remain consistent at n plus m in most scenarios. In the best case, all the initial boxes are already open, and there are no keys or nested boxes to process further. Here, the time complexity reduces to n, because we only process the initial boxes, and the space complexity remains n, since we don't need to store any additional keys or boxes. In the average case, we encounter a mix of nested boxes and keys, requiring more iterations to process, but the overall complexity remains n plus m. Similarly, in the worst case, all the boxes are initially locked, with keys deeply nested inside, meaning we must process every box, key, and nested structure. Even here, the time and space complexities are n plus m, due to the linear processing of boxes and keys. To solidify this, we can mathematically prove the big O bounds. First, for time complexity, each box is processed exactly once, contributing n. The total number of keys in contained boxes across all iterations is bounded by m, contributing m. Adding these terms gives n plus m. For space complexity, the queue, visited set, and collected keys set collectively require n plus m space in the worst case. Additionally, the input arrays contribute n plus m storage. Summing these, the total space complexity is n plus m. This proves that the BFS-based solution is optimal for this problem, balancing both time and space efficiency effectively. When solving this problem, there are a few common mistakes that can trip you up. First, forgetting to track which boxes have already been opened can lead to redundant computations or even infinite loops. To avoid this, always maintain a visited set to ensure each box is processed only once. Next, it's crucial to check for all keys inside a box. If you skip adding these keys or fail to fully explore them, certain boxes may remain locked and inaccessible, potentially leading to incorrect results. Another important consideration is handling circular dependencies. For example, if box A contains a key to box B and box B contains a key to box A, some solutions might get stuck repeatedly processing these boxes. Using a queue or stack with careful checks can help you avoid revisiting already processed boxes. Finally, don't assume that all boxes are initially accessible. Many solutions overlook the fact that some boxes may be locked from the start and only become accessible later when you collect the right key. Always verify whether a box is accessible either at the beginning or as you progress through the keys. It's also critical to handle edge cases properly. For instance, what happens if no keys are provided, or all the boxes are empty, or all the boxes are locked? These scenarios need to be addressed to ensure your solution is robust. Now, from an interview perspective, this problem often boils down to a graph traversal challenge. Think of boxes as nodes and keys as the edges connecting them. Techniques like breadth-first search, BFS, or depth-first search, DFS, are commonly used here. For optimization, instead of repeatedly rechecking all boxes, you should prioritize opening newly accessible boxes. This is where a queue or stack becomes invaluable. You should also be prepared to discuss edge cases with your interviewer, such as handling an empty input, a single box with no keys, or a scenario where all boxes are interconnected. Lastly, consider the trade-offs between BFS and DFS. BFS ensures you open boxes in a shortest path-like order, which is often more efficient, while DFS might explore deeper paths first but can sometimes be less optimal depending on the problem constraints. To deepen your understanding, it's worth exploring related problems like LeetCode 841, Keys in Rooms, which also involves unlocking nodes in a graph-like structure. LeetCode 200, Number of Islands, focuses on connected components, which is another variation of graph traversal. LeetCode 130, Surrounded Regions, and LeetCode 417, Pacific Atlantic Water Flow, further explore grid-based traversal techniques. In terms of alternative approaches, a brute force solution iteratively checks all boxes until no new boxes can be opened. While simple, this approach is inefficient with a time complexity of n squared, in the worst case. A more efficient strategy is to use BFS or DFS, reducing the complexity to n plus m, where n is the number of boxes and m is the total number of keys. For more advanced scenarios, like when certain boxes need prioritization, a priority queue can be introduced. However, this added complexity is often unnecessary for simpler variations of the problem. Understanding these approaches and their trade-offs can make your solution both efficient and adaptable to different constraints. Great job! We've successfully tackled maximum candies you can get from boxes. Remember the importance of BFS for traversal-based problems and how data structures can simplify complex logic. Thanks for watching, see you in the next lesson. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!